Okay, hi class. So today we're moving on to chapter 4, and we're doing section 4.1 first, which is all about exponential functions. So an exponential function is anything that looks like this, where we have, let me do that red over here. So we have a function where the base is a real number that's bigger than 0, and the x, the variable, is in the exponent, so that's why it's called an exponential function. So to give us a kind of a chance to tell the difference why exponential growth is different than what we've seen before, is let's compare the function 2 to the x. Let's compare that to just the doubling function, so the function that just takes every input and doubles it, 2x. So as you can see, I made this table here. When x is 0, 2 to the 0, so 2 to the 0, that's equal to 1. Every number, if you raise to the 0 power, is 1. And if you take the 1, you get 2 to the 1, which is 2. And 2 squared is 4. And 2 cubed is 8. So here you start to see that it really grows really fast. And 2 to the 4 will be 16. And 2 to the 5th is 32. So it grows really, really, really fast. And that's what this table is telling us. So this first function, f of x, we would say that displays exponential growth. Now the second function, 2x, that is much simpler. That just takes this input and multiplies by 2. So 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. And after the 2 here, they really start to diverge. The exponential graph goes really big, 8, 16, 3, 2. The doubling graph just you increase it by 2. You're really just adding 2 every time. Whereas the exponential graph, you're multiplying by 2 every time. So it gets really fast. So the second graph, g, actually just displays linear growth. So it only goes as fast as a line. This is the graph of 2 to the x, so this is an exponential graph. And you can see that it goes really, really fast. It starts to almost be vertical. And if I plotted the next point, 4, 16, it'd be like way up here. And it just goes really, 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 really fast. So some key things about it is that, and this is true, so we'll summarize the behavior for this graph. For 2 to the x, the domain, as you can see, I can plug in whatever I want. So the domain is all real numbers. There's no problem there. The range, as you can see, the graph the graph goes up as far as you want, so it's definitely going to go to infinity. But the smallest the graph can ever get is 0. It will approach 0. It won't actually reach 0. So it'll be 0 to infinity. As you plug in negative numbers here, like -3, -2, -1, all that does is it make a fraction. And that fraction will approach 0, but never reach 0. So that's why the range is 0 to infinity. Notice that they're both soft. Okay, we don't include infinity. We can never include infinity. And also, for this graph, we don't include 0. F of x is always increasing. As you can tell from the graph, it just goes up and up and up and up as you go to the right. F of x has no x-intercepts or zeros. Okay. The horizontal asymptote, you can see, is y equals 0. It approaches this y equals 0 line, but never actually touches it. That's why there's no intercept. That's why it's the asymptote. Remember, you can't touch the asymptote. You get really close to it. The y-intercept for this graph is 0, 1, right here. Okay, and that's because, again, 2 raised to the 0 power is 1. And let's talk about the left and the right end behavior. So over here, this is just talking about the left end behavior. As x goes to negative infinity, what does the graph do? Well, the graph looks like it goes towards its asymptote. So f of x goes to 0. And as x goes to infinity on the right side, the graph just goes up, 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 up to infinity. So As x goes to infinity, f of x goes to infinity. Okay, so what we just did here is true for all functions that look like an exponential, and the general form looks like this: a times b to the x. A is called the starting term, or initial value. Your book uses different language here. Okay, and b is called the base of the exponent, so just call it the base. Your book also calls it the growth factor. Okay, so basically anything that looks like a real number, a is a real number, b is positive, and you have it to an exponent. Now, for all those graphs, they all have the same summary here. Okay, the only thing that changes might be the asymptote, but that's it. Well, actually not the asymptote, sorry, the initial y-intercept. Okay, so let's just make sure we're doing okay. I'll try to keep it here. So which of these are not exponential functions? Remember, an exponential function looks like this: a times b to the x. A is real number, b is positive. So take a look at these, pause the video, and see if you can identify which is which are exponential functions or not. Okay, and we're back, and so this one is not. Okay, that's because it's a polynomial. See where the variable is? The variable's in the base, not the exponent, so that's not one. This is. Okay, a is 1 in this case, and b is 1/3. My pen's having trouble. Okay, well anyways, b is 1/3. This one is not. Okay, and that's because a here is -1, and sorry, not a, but b is -1, which is not allowed. So we have to have b being positive, and that is not positive, so it's not allowed. And this one, 4 times t, 4 to the t minus 2. Now this doesn't look exponential right now, but we can do some algebra here. This is the same thing as 4 times t times 4 times -2. That's just algebra rule. And this becomes 4 to the -2, that's 1/16. And so this actually equals 1/16 times 4 to the t. And so now a is 1/16, and b is 4. And so yes, that's an exponential. Okay, so let's get practice evaluating. So we want to be able to just understand what the heck we're talking about when we plug in numbers here. So this first one here, so this we have a function that's an exponential. It looks like 5 times 3 to the x plus 1. Okay. And right now this doesn't look like an exponential form, but remember, if I just add a +1, all that does to the graph is it just moves it to the left. But if you don't like that, you could rewrite this as, oops, let me get my pen back. You could rewrite it as 5, let me do all this. Delete all that stuff. Okay, so now we're back. So you could rewrite this as 5 times 3 to the x times 3, which is just equal to 15 times 3 to the x. Yeah. Okay. Either way, you could evaluate it straight from here, or you could evaluate it here, no problem. But let's evaluate f of 2. So f of 2, I'll go back and just do it from the original. F of 2, we're going to get 5 times 3 to the 2 plus 1. Remember, of order of operations, you do 5 times 3 to the 3, which is 5 times, and 3 times 3 is 9, and 3 times 9 is 27, so it's 5 times 27, which is 135. Okay, so that's the first one. That's f of 2. F of negative 2, let's take a look. We plug in 5 times 3 to the negative 2 plus 1, which is 5 times 3. Negative 2 plus 1 is going to be negative 1. Remember what a negative exponent does. It flips it, so it's 5 over 3. And that's it, that's 5/3. Nothing you can really do there. Okay. Let's take a look at application. Exponentials are really used a lot when we're talking about stuff that grows with constant growth. So if something always goes up by 1% every year, so like economies, US goes up by about 2.5% every year. It grows by 2.5% every year. Also, if you have like a savings account or investment account, they go up by a percentage growth if you get a return, positive return. So those are all modeled with an exponential growth equate function. And so like this one here, it says we have the population of India, and they are growing at an annual rate of 1.2%. Let me get back right here. 1.2%. Okay, and they had an initial population of 1.25 billion. Okay, so we can use that to make the model, and I'll write it right here, for their growth. P of t is equal to, remember we always put the initial amount here, so 1.25, and then we put this right here, 1.012 to the t. Okay, and the reason it's 1.012 is that if they're growing by 1.2%, first things first is convert that to a decimal, so that's going to be 0.012. That's how much they're growing every year. But if they're growing, then we have to add that to their original amount, and the original amount is like 100%, 1. So we add that to 1.0, and we get 1.012. This is the growth rate, the growth factor. Basically, this is the b in the b to the x, or the b to the t. So that's why this gets put right there. Okay, so that explains it. Now, be careful, remember, this is a model, so we have to be careful what t represents. T here represents, and I'll put that right here, t is years since 2013. Remember that. We always have to define our variables and talk about the context of the problem. So then we can actually ask the question. It says, according to the model, what will the population of India be in 2031? Okay, so in 2031, what's going to be the population? Well, first we have to figure out what is that time. Well, remember, we're always doing it with reference to 2013. So if I take 2031 and I subtract 2013 from that, I get 18. And so my t is actually equal to 18 here, not 2031. And now that I know my time, I can then plug that in. So p of 18, that's going to be the population in 2013. Sorry, not 13. In 2031. And so then we just plug it in. So p of 18 is equal to 1.25 times 1.012 raised to the 18th power. Now, let me show you, make sure you're okay on this calculator stuff. So when you want to plug it in, you want to do it exactly like it's written. Your calculator can understand it. So 1.025 times 1.012 raised to the 18th power. Like that. And we get 1.549. So we get 1.549. 9. And remember the units, the population was in billions, so this is going to be billion people. So in 18 years from 2013, so in 2031, the population has grown to 1.549 billion people. Okay, let's do one more, make sure we're okay, and we can do it from a chart as well. Just remember, anything that has percent growth, where it grows either the growth rate is constant, the percent growth rate is constant, then we use an exponential model. And this one I had told you anyways that it was an exponential model. So since I know it's an exponential model, I can go ahead and write out what the basic form of a model is. They said they wanted an n of t. So I know my model has to look like this. N of t is equal to some first number times b to the t. Okay. Now remember what a is. A is our initial value. So we get to choose what we want to start at. Here it says in 2008 there were 11.63 million. And I included a chart here for you. iPhones. So why don't we start here? So why don't we call that t is equal to 0? That's the starting value. So if t is 0, that means that this is a. A is your starting amount. And so I know that my model looks like this now. N of t looks like 11.63 times the base, which I don't know, raised to the t. So you can always find your first amount just by zeroing out your time. And so when time was 0, I chose this one just because that's where the problem started with in 2008. This chart I just pulled up from the internet, but the problem was started with 2008, so that's a better thing to start with. What's given. And these are actual numbers, by the way. There's only 11 million iPhones in 2008, and now in 2012 there's 125. It's crazy. So, and it does look exponential, FYI. So it's growing like that. Okay, so how do we find b? Well, the way we do that is we just use another value. So the answer is use another coordinate. So in this case, they told me another coordinate. They said 2012, that's the input, and the output was 125.05. So we can use 2012 and 125, but remember that 2012 has to be relative to where we started. So if 2008 is 0, then 2012 is going to be 1, 2, 3, 4 away. So 2012 is going to correspond to t is equal to 4, because it's 4 years away from our starting point. So t is equal to 4. So now we have t is equal to 4 as our coordinate. And our coordinate pair is going to be 4, 125.05. And we can just use that value to plug it in. So this is a t, and this is an n of t. Okay, so we just plug it into this model, and we get 125.05 is equal to 11.63 times b, we don't know b, raised to the t, which is to the 4th power. Okay, and then algebra we want to do to solve this, we want to isolate b, so we got to divide both sides by 11.63. Divide both sides by 11.63. Those cancel. And I have to use a calculator here. So 125.05 divided by 11.63 is equal to 10.7523. So we get 10 point, I already forgot. Never get old. Okay, you forget everything. 7523 is equal to b to the 4th. All right, and then how do we solve this? Well, we want to get rid of that exponent. So we just do the opposite square root. So we'll do the fourth root here, and we'll do the fourth root here. Okay, and now we're going to solve for b. And the way you do that is you just take this number and you raise it to the 1/4 power. That's what a root is. So raise it into the 1 over n power. And so you get 1.8108. And so you get 1.8108 is equal to b. And just just to show you again on the calculator, remember the way you do a root is to the 1 over whatever the root is. So if it's a fourth root, it will be 1 over 4. That's the exponent for it. Okay, and so now we're done. We just plug it back into our model because the question was just asking us to find the model. And so now I know my model is n of t is equal to 11.63 times 1.8108 raised to the t. And of course this is an estimate, but it's a pretty good estimate. And what this also tells me is that the percent growth year over year is right here, is the decimal part. So that's going to be 81.08%. So quite fantastic. So if you had invested in Apple back then, man, you would have done really well for yourself. Because it grew at 81% every year over year, which is fantastic. Okay, so that's how we work with those problems. When you have a base, an exponential, you just got to find the a and the b. Okay, you have to find the a and the b. And you find the a by finding the initial value, like I did here. That's a. And then you find b exactly like I did. You just use another coordinate to find it. Okay. So we're going to move on to one more type of model that we're going to use. It's called the compound interest formula. So when you have any bank account or savings account or interest giving account, this is the formula that governs how much money you're going to have. A is the amount of money that you have at a given time. So this is the bank account number, or the what's in your investing account. T is always in years. You never do months or anything. P is the starting amount. It's called the principal. So again, that's the initial amount. R is the annual interest rate, and that's always expressed as a decimal. So make sure that you convert that to a decimal. And N is the number of compounding periods. So in real life, you only can compound once. It's called simple interest. There's not many. In reality, there's not many brokerage firms that will give you quarterly compound interest, but there are some. There are some accounts where you can compound quarterly or more than once a year. So if you only compound once a year, then once a year, that means n is equal to 1. But if you do it like semi-annually, okay, that's twice a year, so your n will be 2. If you did it quarterly, that means you do it 4 times a year, so your n is 4. Okay, monthly, your n is 12, etc. Okay, weekly, your n will be 52. Daily, your n will be 365, etc. So let's take a look at this problem. So we want to invest $3,000 in an investment account paying 3% interest compounded quarterly. So I see 3 things right now in the problem. 3,000, that's going to be my principal. I see 3%, so that means 0.03 is going to be my R. And compounded quarterly, that means my n is 4. And then they tell me that how much will the account be worth. They're asking how much will the account be worth in 10, so my time is 10. And so then I just plug it into the formula. So I get A of t is equal to 3,000, 1 plus 0.03 divided by 4. My pen 1.3 divided by 4, raised to the, now there's an n up here too, okay, so it's 4 times time, so it's 4 times 10. And so that's the model. Just to help you, this is P, this is N, this is R, this is N, and this is time. Okay, now we just got to do this in our calculator, so hop over there, and you can plug it in straight away, which is really nice. You can just do 3,000 times 1 plus 0.03 divided by 4. Oops, missed the divide sign. 0.03 divided by 4. Okay, raised to the power of, put that in parentheses, 4 times 10. Okay, and then we hit enter, and there you go. So $4,045.05. That's what our account's going to be worth. It's 5 cents, right? Yeah, raise the 4 up to a 5. Okay, so pretty good haul. After 10 years, we've increased our amount by $1,000. That's pretty good. Okay, so that formula you do have to know. Okay, I'm going to expect that you can do it. We ask our algebra students to do that here at LMC. So you know, that formula is just remember to have that in your back pocket. Okay, and just refer to it as you do your problems, but with the goal of trying to memorize it. And the last thing is we want to talk about is the number e. So this number e is one of the most important mathematical numbers, or just numbers in general. It's like pi, that it's a constant. It has a value. You know, pi is 3.14. You know, 1591. Blah 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 blah. So e is a number 2. It's 2.718. I can write that right here. Actually, it's right over here. 2.718 28 45 90. Oh, I messed that up. It's been so long since I've written this number out. A couple weeks. But anyways, 2.718 28 18 18 28 45 90 45. So anyways, we can just always approximate it as 2.718. This number, it comes from the definition, from this definition, and this doesn't come out of nowhere. This actually comes from this formula right here, the compound interest formula. If we compound over and over and over again, so compound every nanosecond, then that growth converges to this number, which is 2.718, which means we have 171.8% growth. And that's the fastest you can grow. So it's kind of weird, but if you compound over and over and over again, every second, every nanosecond, every femtosecond, as fast as possible, we call that continuous growth, continuous compound growth. Well, then it doesn't matter. You're limited by, this is as much as you can grow, this number e, which is pretty cool. Okay, well, let's just get practice. We're going to see this number e a lot throughout this chapter and through the rest of the semester, but let's just get practice of what it entails. So e to the 3.14, let's just get practice evaluating that. Oops, wrong button. You just go over here, and if I want e, so if you just want the number e, it's right here above the division symbol. So I'll do that again. It's right above the division symbol on your calculator, so that's e. And so e is 2.718281828, like I said. But if you want to raise it to an exponent, then you have two options. You can say, okay, I want to do e, and I want to raise it to, in this case, the problem wants 3.14, which is that 23.103, 86, whatever. But there's another way, there's another button. So if you want to do e, you can actually, it has its own button right here. So you hit second, and you do the button right above ln, which is on the bottom left here, and that will do an exponent for you right away. So if you want to do an exponent of e, just do it. Just do that button. I'll do it again. It's second ln, like that. And then you raise it to your number, to your exponent, which is 3.14, and you get that. You get the same answer, 23.1038. 103 was a 9, because that 8 is followed by a 6, so rounds up to a 9. Okay, this is just a preview of contractions. We're going to see E a lot throughout this chapter, so we'll definitely get practice with it. All right, thanks everyone. I'll post these on Canvas, and you can start the homework now. Thanks.